after watching that, come back to Newton's three laws. Let's discuss them. Again, remember, rocket launches like that put all those laws together into one nice little assessment question. Right? And a good one. So I want to discuss it now, and I'll record it and put it up to YouTube for future downloading. All right. So first of all, first law. Where does that come in? Law of inertia. Objects in motion will stay in motion. Objects at rest will stay at rest unless there's an outside force. There's only one real spot where it's going to kind of come in. It's obvious. Takeoff, the launch. So as this thing just starts to launch, you can look at it, you can kind of see it launches relatively slowly for the sheer amount of force that's acting on this thing, which is lots, and I don't know what number, I'd have to look it up. But it launches slowly. It has to overcome all of that inertia first. So Newton's first law comes in at the first. Objects in motion stay in motion, objects at rest. The rocket is at rest. It is extremely massive. Okay, remember, it's doing half a ton of fuel per second. That's when it's up in higher, close to orbit. Right? So there's a lot of fuel there. There's a massive amount of matter. So there's first law. We'll skip the second for a second. Let's go to the third. Newton's third law, extremely important for a rocket to work. Where does Newton's third law come into play? What do you think? For every action, there's an opposite and equal reaction. So where there's a force, there's an opposite and equal force.
Excuse me?
Yes.
Is James MacDonald there?
Yes.
Would you come to the office for a moment?
On our way. What's that? So a third law, where does it come in? It's definitely there. It's the whole reason this thing can really get to space. The rockets themselves. Yep, the rocket boosters themselves. So let's go into a little bit more detail. Where is that opposite and equal force happening? What's making the rocket go up? What's that? The propulsion. What's the direction of the propulsion? Downward. So the thrust from the rockets is downward. Equal and opposite reaction to that is going to be up. So inside of this chamber where the explosion's happening, inside that chamber, rocket exhaust is coming out downward. An opposite force inside that chamber is pushing the rocket upward continually. Okay? As long as there's thrust down here, there's going to be an upward force from each engine, from each part. So does it push off the ground? Does the rocket, folks?
7, 6.
Does the rocket push off the ground? Is there an equal and opposite reaction force? Is it pushing off the ground?
Yes.
It's still pushing off the ground. So right now the rocket is pushing upwards because of the force bouncing off the ground. No, it took a bit, but you got it. No, it's right. Absolutely not. It is starting to be kilometers up in the air. It is not pushing off the ground.
But it was at first.
A little bit, yes. Yes, a launch pad is definitely more efficient use to launch a rocket from than no launch pad. So if you had this rocket positioned 30 feet up in the air, it will be a less efficient launch than if it was launched closer to the ground, so you can actually get a bit of backfire or Newton's third law from the launch pad. Stop this. And I just wanted to clarify that because I would always get answers on a test that the exhaust and the rocket would be propelled from the opposite force off the ground. It is not off the ground at all. It is outside of those rocket boosters, right? The actual rockets themselves. Second law. It's the one we've been working with lately. Net force equals mass times acceleration. Now, we're not concerned with, the net force necessarily as people would be, well, how fast? We need to get up into orbit, you have to be going fast. You heard it. By the end, it was going to be going 5 miles per second. So times that by 1.64, roughly 7.5, close to 8 kilometers every second. Okay? It's like 1001. I'd be home. Done in 1 second. So very quickly. So I'm going to rearrange this. Think about acceleration. Net force divided by mass. When those exhaust boosters are firing and when those rockets are firing, do you think the force of thrust changes much? Or is it pretty consistently the same? So the exhaust coming from those thrusters, that chemical reaction that's happening, do you think it's pretty much consistent net force acting on the rocket? Or do you think it's changing a lot? So the chemical reaction doesn't change too much. You're always adding the same amount of reactants. You're always going to ignite them. You're always going to get the same amount of force out of that, same amount of explosive force, right? Pretty consistently. So even if the same thing in your car, right? As you're driving a car, or as you will be as you get older, and if you've got half a gas tank full of gas, so if your gas tank is half full and you hit that gas, you're still going to accelerate as if, for the most part, if the tank was full, right? How much gas is being used in the engine is going to be the same, right? Pretty closely the same. So the same thing here. As long as there's some fuel in there, it's always going to react. Now, for the most part, I think a lot of this fuel is liquid hydrogen, liquid oxygen. So hydrogen, very explosive. You might have seen the Hindenburg blow up video, right? One spark, hydrogen, boom. A lot of chemistry accidents in high school happen because they're trying to separate the hydrogen and oxygen in water. Then you take the hydrogen, you put a little flame to it, and a little mini explosion. If done unsafely, it can definitely blow up a glass beaker. Well, this is liquid hydrogen, and lots of it, liquid oxygen, so it's really cold. And so they come in, you ignite them, boom. Right? They are sitting on probably one of the world's biggest explosives and riding it to space. So the net force from launch to orbit until the boosters kind of separate pretty much stay about the same. Okay. What do you think the acceleration does as it launches from launch pad up to a point, before those boosters come off? Does acceleration stay the same? Does it get less? Or does the acceleration increase? What do you think? Acceleration still. Think about the formula. We've kind of said the net force stays about the same. Does the mass stay the same? Does the mass of a rocket stay the same if it's burning half a ton per second? Nope, not at all. So, and this is how rockets are able to gain so much speed so quickly. Net force stays the same, but mass is decreasing. And when you do that division, when you divide by a smaller and smaller number, what's the result get? Keeps getting bigger. So the acceleration is not constant. If you were sitting on this thing, you would start to feel a greater and greater kind of force against you, greater and greater acceleration. We're not used to that. We don't experience it. If you go on a carnival ride and it's spinning in a circle, it's usually spinning at a constant rotation rate. So you feel a different force, but it's the same. In the rocket, it's going to continually increase, okay? Greater and greater and greater, until maybe the thrusters come on.
Any grade 10 students who need picture retakes are asked to go to the library now.
So to summarize, Newton's second law comes in by knowing acceleration is net force over mass. Because the mass decreases, the acceleration is going to increase. So the change in velocity is not constant. It gets faster and faster and faster. So it in itself changes. And we don't do problems like that. We don't have the math. Once you guys do a little bit of calculus, that's how you handle a situation like this. But even there, the math isn't crazy. I've seen it. It's not too bad, but just haven't done it yet. All right, good. Stop. All right. So this question's a little different than the one we did last time, I guess about a week ago. So again, hopefully you were spending some time reviewing this stuff, because I'm not slowing down. So undergoing an acceleration at 750 kilogram car's velocity goes from 21 meters per second east to 15 meters per second west in 7.5 seconds. So a couple of months ago, this would have been a normal question about kinematics, calculating things like where did it end up, What was the acceleration? How fast was it moving in 3 seconds? Those kind of questions. We're connecting it now with Newton's second law. So the first question here isn't anything about acceleration or position or time. It's calculate the average or net force. So those two words we'll use interchangeably for our math formulas. Calculate the average force acting on the car. So hopefully we get around negative 3,600 newtons. The question says nothing about acceleration. So let's just approach it. We want to try and figure out what acceleration is. Nope, sorry. The question's asking us for force, net force. Writing down everything that we had. Initial velocity, 21 meters per second. I'm going to say that's east. Set up my coordinate system. East positive, west negative, usual. Again, remember, if you want to switch it around and have west positive and east negative, just make sure you've clearly shown so. Okay, otherwise, I'm just going to assume east is positive. You've got to be specific. Final velocity is negative 15 meters per second east because it is going west. So again, it's been a while since we've had those kind of questions. Just like friction is opposite motion, this final velocity is opposite its original motion. What else do we have? It's mass and time, 7 seconds, 7.5. So we're asked to solve for net force. There's two relationships for net force we could look at. The definition, sum of all the forces, or Newton's second law. And this happens often. We're at a point now where we've got lots of mathematical relationships. Depending on what's given in the question or depending on what's asked, there could be multiple ways of solving for that. So you have to pick the one that matches correctly. So net force is the sum of all the forces. We are not told anything. Take a look at the list on the left. No force of friction, no normal forces, no applied forces. We don't have any of that info. So we're not going to be able to do kind of the sum of the forces, right? No info on that stuff. So this leads us with Newton's second law. Now, it's not straight exactly mass times acceleration. To look at the question and realize I'm not given acceleration, but with what's there, I can calculate it. So really the entire problem boils down to finding and calculating the acceleration. Once you find that number, multiply it by 750, and you are done. So let's find acceleration. If you check your handbook for a formula for acceleration, there's 3 of them. 3 formulas that contain acceleration in them. So now you got to start picking the right one, which is going to match the situation that we've got here. We have initial velocity, final velocity, and time. Starting in from the right, we've got initial velocity, final velocity, but this has position information in it. That's no good to us. We're not given anything about position. Next one over here, time. We have time. We want acceleration. We have initial velocity. Once again, there's position information needed. We don't have that information. We're trying to solve for A, which means we have to put a number in for everything else. We do not know the final position. So hopefully the last one's going to work. We have time, initial velocity, final velocity, and we solve for acceleration. So we're going to use this one. And this is the definition of acceleration, change in velocity of time. So that's the formula I'm going to use. Final minus initial over time. Final, be careful, negative 15 minus initial, 21, divided by 7.5. So negative 36 over 7.5, negative 4.8. So that was most of the work. Always remember to go back and check the question, what you're asked for. Many people will do this question on a test and all of a sudden their answer is negative 4.8 meters per second squared and not actually figure out the force. So go back and make sure you do that. Force is MA, which is 750. On the acceleration, which is negative 4.8. Negative again because it's going from east to west. Right? It's changing direction. It ended up going west, so it's got to be negative. So rounded to a couple of digits, significant digits, 3,600 newtons, negative 3,600 newtons. Now we've got our answer. Questions on any of those steps, mathematically or otherwise? I'm not going to worry about answering calculation number 2. It's the same formula for position as the other problem, so you guys can try that one, see if it works out to 225. Just one good thing to note, though, is that even though this object at the end of 7.5 seconds is traveling west, it is still east of its starting point. Right? Remember how those directions can work. So there's one more I want to do. So take a look at this one. So this one, we've got an object falling and it's landing on a mattress, and all the information you're given, folks, all the information you're given is about what's happening at this mattress. So you can kind of picture it. If you've seen stunt people jump off buildings, they land on an air mattress. That's kind of the situation, except it's not a person. It's a 2.5 kilogram ball. Just before it hits the mattress, the speed is 19 meters per second. So notice I don't tell you the velocity, because depending on how you choose your directions, which way is positive, which way is negative, that will affect whether the 19 is positive or negative. So I just use the word speed. The air mattress depresses or squishes 0.75 meters to stop the ball. We want to calculate the average stopping force. Like last time, just to save a little bit of time in explaining it, we cannot calculate net force by adding up forces. There's no friction, there's no air resistance, none of that kind of stuff. It's just information about how it's moving and where it is. So the first thing we're going to do is try to solve for the acceleration. Find the acceleration first, then use F equals ma. That's what we're going to do. Boom away. All right. So do a diagram up. You're most likely going to make a mistake with setting this problem up if you don't have a diagram. And it does not have to be elaborate. Mine will be terrible. There's my air mattress. And it's going to compress. It's actually one of my better air mattresses. What's that? Yeah. I just need it big enough to label. So it falls within the air mattress 0.75 meters, 75 centimeters. Just as it hit its velocity magnitude, I'll put absolute values there, is 19. How fast is it moving when it comes to a stop? That's the easy part. Its velocity down there, which of course is, I can't draw, its magnitude is 0. It's come to a stop. So it starts by going 19, it falls 0.75 meters and comes to a stop. Trying to figure out the acceleration. The important part for us is going to be the coordinate system. So for its motion, I'm going to say up is positive and down is negative. Usual, just like our graphs.
Please excuse the interruption. Would students in grade 11 and 12 who need picture retakes please go to the library now? That's 11 and 12 students who need picture retakes. And reminder to the field house team that your picture is at 12 o'clock today in the gym.
So that makes initial velocity negative 19. Comes to a stop, final velocity 0. Now, what's the initial position and what's the final position? Let's not worry about his hair right now. What's the initial position? What's the final position? Is the initial position 0.75, final position 0, or is the initial position 0 and the final position related to that 0.75? That's up to you. Remember when you did your analysis videos last week, You hit the coordinate system button. A coordinate system appears, the purple line. That horizontal purple line is your x-axis. Anything above it is positive, anything below it is negative, but the line itself is 0 vertical position. That's where you have to decide where is 0 vertical position. Girls in the back, phones away for 5 minutes, please. Where is that 0 0 position? Yeah, you can pick. It will work either way. So is your 0 position at the top of the mattress where it would be uncompressed, or is your position 0 at the bottom of the mattress where it comes to a stop? Any preference? Any thoughts? Where it comes to a stop, sure. Period 2 we did the other way, so this would be a good mix. So that's our position reference line. Right, so position is 0 at that line. That makes initial position where the ball just hits the top. Here's our ball. It's falling down. 0.75 meters. Positive or negative 0.75? Positive because it is above the line. Final position becomes 0, because that's where it stops. And remind you, we are looking for acceleration. So now we've got our numbers. And I told you it was all about that 0.75. When we did it in period 2, the red line was up here, making the initial position 0 and final position negative 0.75. Both methods will give you the same result, but you might put that 0.75 in the wrong spot. Right? So now we have our things. We can go to our formula and save a little bit of time. The formula that best matches everything that we're given is this one. Final velocity squared is the initial squared plus 2a times your change in position, final minus initial. But we're not given the time it takes for this thing to come to a stop. You could solve for it in theory and then use that to figure out the acceleration, but we're not going to worry about doing it that way. Putting our numbers in, final velocity is 0. Initial velocity is negative 19. Trying to solve for acceleration. Final position is 0. Initial position, 0.75. 0 squared, 0. Negative 19 squared is 361. 2a times negative 0.75. No matter how you set up your reference line, you would always end up with a negative 0.75 in there. So if you ended up with a positive 0.75, that's when things go wrong. Remember, this is the change in position. The object is falling downward. The position change has to be negative. So I'll bring the 361 to the other side, becomes negative. 2 times 0.75 is negative 1.5. Dividing both sides to give us acceleration. I think that works out to be 241 meters per second squared. And then just to beat the bell, net force equals the mass of this thing times that acceleration. 241, if I can write it right. Oh. 1. Good enough. Thanks. Multiplying those, you should get around the negative. Forgot my negatives and no positive. Positive. Trying to go too fast. No negatives. Positive 602 newtons to stop. So think about the direction, whether or not it makes sense that it's positive or negative. Review this one again quickly tomorrow.